Hello everyone. The first law of thermodynamics was completed in the last lecture, lecture number 17. Now it's time to apply this first law in chemistry, and this part of application of thermodynamics in chemistry is also known as thermochemistry. This lecture on thermochemistry is divided into two parts. In part 1 we are going to discuss the laws of thermochemistry and some basic terminologies. But before that, let us define what about thermochemistry and how H or delta H is also known about. The study of heat change involving a chemical reaction is thermochemistry. So this is a simple definition. The study of heat change. When a chemical reaction is taking place, heat may be absorbed, heat may be released. So that determination of that amount, calculation of that amount, okay, both theoretically and practically. So this is thermochemistry. Now, most of the chemical reactions in the laboratory, what you are performing, all are taking place at constant pressure, because the atmospheric pressure doesn't change. So, as per the first law of thermodynamics, the deductions from the first law mathematical form, you have come to know that QP is nothing but H. So all the heat changes involved in any chemical reactions are enthalpy, or their change are enthalpy change. So since most of the chemical reactions take place in the laboratory where the entire pressure of the system remains unchanged, therefore most of the heat changes or energy terms are enthalpy or its change delta H. Now this delta H has different terminologies. Okay, lot of terminologies. Here I have listed a few of them, but it is also it has some more terminologies out of this. So it may also be called heat of reaction, heat of combustion, heat of hydrogenation, bond energy, dissociation energy, heat of neutralization, heat of formation, heat of atomization, latent heat of evaporation, latent heat of fusion, resonance energy, stabilization energy, heat of transformation, etc., and many more. Okay, now move on to the first law. The first law was devised by Laplace and Lavoisier. So according to the name, this law is also known as the Laplace and Lavoisier law, and this law states that the heat change accompanying a chemical process in one direction is equal in magnitude but opposite in sign to that accompanying the same reaction in reverse direction. Suppose a chemical reaction, A is the reactant and B is the product. In that case, if heat change involved is plus Q calorie, then if the reaction takes place in the backward direction, such as B is the reactant now and A is the product, in that case the heat change should be just same in magnitude Q, but its sign should be opposite, that means minus Q calorie. So it's simple. Okay, and we can also derive from the first law of thermodynamics some more equation which can be applied in thermochemistry also. So we know, according to the first law, delta H equal to delta U plus P delta B, and also delta H is QP and delta U is QV. Okay, now if pressure and temperature are kept constant, then from the equation PV equals to nRT we can also write V equals to RT by P into N, or this RT by P is some constant, since pressure and temperature are constants. Okay, and this is denoted as K. So K is a constant which is equal to RT by P. Therefore V1 must be RT by P into N1 and V2 must be RT by P into N2. That means at two different number of moles, they have two different volumes. Okay, if there is n number of moles in the gas and V1 is the volume, then at the same temperature and pressure, if the number of mole changes to N2, then its changed volume would be V2. Therefore, if V2 is the final volume, then the volume change V2 minus V1 must be RT by P into N2 minus N1. In that case, we can write delta V equals to RT by P into delta N. Delta N is N2 minus L1. Therefore, in this equation, P delta V can be substituted by the term delta N RT. Okay. So here at constant temperature and pressure, we can also write this equation delta H equals to delta U plus PdV as delta H equals to delta U plus delta nRT, and this equation QP equals to QV plus P delta V. This can also be written as QP equals to QV plus delta nRT. So simple derivation. These equations will also be applied. Now the second law, it is known as the Hess's law of constant heat summation, after the name of a Russian scientist and Dr. Germain Hess. This law is also known as the law of constancy of heat. This law states that for a given chemical process, the net heat change will be the same whether the process occurs in one step or in several steps. So suppose A plus B are reacting to produce X, and the heat involved is Q calorie. Now if this reaction takes place in two steps, such as A plus B prime equals to X prime and then X prime plus B equals to X, then the heat involved in the two steps separately, if they are Q prime and Q double prime, then Q must be equal to Q prime plus Q double prime. As for example, we take another example such as carbon plus O2 equals to CO2. Okay, and here in another process, carbon plus half O2 equals to CO, and in the second step, CO plus half O2 equals to CO2. So carbon dioxide is being produced in two steps. Then the overall enthalpy change of these two steps, if they are summed up, then that would be equal to the heat change that was involved in a single step reaction. So this is the second law of thermochemistry. Now the Kirchhoff's equation. This equation actually describes the temperature dependence of delta U and delta H. Suppose if a system undergoes a change from a given state to another given state, then both internal energy and heat content would alter. And if F and I denotes final and initial states of the system, then delta UF minus UI is delta U and HF minus HI equals to delta H. If both sides are differentiated with respect to temperature at constant volume for the first case and at constant pressure for the second case, then the results are the rate of change in U final with respect to temperature at constant volume minus the rate of change in U initial with respect to temperature at constant volume, resulting in CV final minus CV initial, that is delta CV. Similarly, del H F del T P minus del H I del T P equals to Cp final minus Cp initial, resulting in delta Cp. Okay. Now if this initial state is the STP and final state is any temperature T, in that case you can also write integration 298 to T of delta U equals to integration of 290 to T of delta Cv into dt. This dt comes to the right hand side, resulting in delta ut equals to, that means the change of delta U at any temperature, that means the actually delta U at any temperature equals to delta U0, that means standard delta U. Okay, integration 290 to T delta Cv dt. Okay, this is one of the Kirchhoff's equation, and for in case of enthalpy you can also write delta HT equals to delta H0 plus integration 290 to T. This is the standard temperature and this is any temperature. Integration of what? Delta Cp into dt. Okay. So these two are the Kirchhoff's equation. If Cp and Cv remains unchanged in the temperature range what you are studying. Okay. So these two are Kirchhoff's equations. Now if Cv and Cp values of the reactants and the products remain constant in the temperature range studied, then the Kirchhoff's equation becomes this one. That means the final temperature is T2 and the initial temperature is taken to be T1 here. So the same equation is repeated here. Delta UT2 minus delta UT1 equals to delta Cv. This Cv term is now taken out of the integration sign. Look here. From this equation also you can write delta Cp into dt or delta Cv into dt. So here it was inside the integration term. Okay. Here also it was inside the integration term. But if Cp is constant, then you can take it out of the integration sign. And the same for Cp also. So we are taking it out of the integration sign. Because second time we shall do the same integration with taking Cv, delta Cv inside the integration sign. So this is the first time where Cv and Cp values are constant, okay, over the temperature range what is being studied. So in that case, you can take delta Cb and delta Cb out of the integration, and the result is delta Cb into T2 minus T1, and here also delta Cp into T2 minus T1. Okay, but if Cp and Cb are not constants in the temperature range studied, then they have some different expressions. Both Cp and Cb has some expressions, a plus bt plus ct square plus dot 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 dot. Okay, and their differences, delta Cb or delta Cp, a2 minus a1, that is, this is the final, this is the initial constant, and this is b2 minus b1t, c2 minus c1 t square, etc. But ABC are different for Cb and Cp, so we are getting here where ABC etc. are two different sets of constants. So for Cb it has own ABC values, for Cp it has also its own ABC values. Okay, and the two equations in that case, look here, this delta Cb now inside the integration sign. Okay, and instead of delta Cb we are putting this value. Similarly for delta Cp also we are putting this value. And if a2 minus a1 is written as alpha, b2 minus b1 is written as beta, and c2 minus c1 is written as gamma, then we can get this form. Delta ut2 equals to delta ut1 integration t1 to t2 alpha plus beta t plus gamma t square plus dot 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 c dt. And for delta h also the same expression, but alpha beta gamma, two different sets of constants. That means for Cb, alpha beta gamma has their own its own value, and for Cp, alpha beta gamma has its own value. They are looking here same, but they are different. Okay, that is why we are using the term two different sets of constants. Okay, so that's all about Kirchhoff's equation. Now move on to the terminology, heat of reaction. This is written as delta H reaction in the suffix. So the difference between the sum of the enthalpies of the products and the reactants is termed as the heat of reaction, or in short, delta H reaction. So simple, the enthalpy of the product minus enthalpy of the reactant. This is delta H reaction and enthalpy of the product as well. Here, look back. This is enthalpy of the product, enthalpy of the reactant, and in general, it is enthalpy of the substance. So enthalpy of a substance, that means that a product or that of reactants at a certain temperature and pressure, is obtained by calculating the overall heat change due to its transformation of that substance to that state from standard state. That means it is at standard state, and at any temperature and pressure, arbitrarily chosen temperature, arbitrarily chosen pressure, it has transformed. So due to this transformation, the heat involved, if calculated, then it is the enthalpy of transformation. So suppose X is such a substance which was at STP and has now attained any temperature T and any pressure P. These two are arbitrarily chosen temperatures and pressures. Then its enthalpy at that state is calculated as this one minus this one. Okay, this one is the final enthalpy, and this one is the initial, which was at STP. So the difference between these two. So this way the enthalpy of a substance is calculated. Now after enthalpy, what about the standard enthalpy? Look back here again. This is standard enthalpy. So from here, the enthalpy of the substance, enthalpy of the reaction means enthalpy difference between the product and the reactants. In general, enthalpy of the substance. Then enthalpy of a substance. Enthalpy of a substance means the change from the standard state. Now what about the standard state enthalpy? That means H0F. Okay. So the enthalpy change occurring when a gram mole of substance is formed from its constituent elements available in the most stable state at STP is called standard heat of formation. That means the state should be STP, standard temperature and standard pressure. Not only that, the constituent element at its most stable state. From that state, the substance for what the H0F value is going to be calculated, the heat involved from the most stable elemental state to that substance is called the H0F, or the standard heat of formation. So the H0F value is taken to be 0 for the pure element in its most stable state. Here it is elaborated. Most stable state means the state having the lowest energy, as for example in graphite for carbon, O2 for oxygen, or rhombic sulfur for sulfur, red phosphorus for phosphorus. Carbon has a lot of allotropes such as diamond, charcoal, graphite, but out of this, graphite has the lowest energy. So this is the most stable one. Okay. Then oxygen, O, O2, O3. O2 is the most stable. Sulfur, rhombic sulfur, monoclinic sulfur. Rhombic is the most stable. So the substance which has transformed from this most stable state to the other any substance, and the heat involved in that process is called H0F of that particular substance. So this way, from H0F to H, then H to delta H. So let's elaborate this with some examples, such as standard heat of formation of oxygen atom. Okay. So the bond dissociation energy of O2 at STP is 498 kilojoule per mole. Therefore, the H0F value of oxygen atom, or half O2 is the oxygen atom, is just its half. Okay. 498 divided by 2, that means 249 kilojoule per mole. How is this calculated? O2 is the most stable elemental form, so it should have the H0F value 0 as defined earlier. And what is the H0F value of O? We do not know this. So let us suppose that value is H0F, and this is multiplied by 2 for 2 number of species. Okay. And the delta H of this transformation has been calculated to be 498 kilojoule per mole. So this is nothing but H0F of the product minus H0F of the reactants. So what is the value of delta H0 of the product? Now it is 2 into H0F of half O2. And what about delta H0 of the reactant? Now it is H0F of O2. But we have arbitrarily taken this value as 0. Okay, this is the standard, and this is always considered as 0. So this H0F value is nothing but obtained from this delta H reaction. Okay, so H0, what is the H0F value of 1 O atom or half O2? Now it is 498 divided by 2. That means this one divided by 2. This way, 249 kilojoule per mole is the standard heat of formation of oxygen atom. This way it is calculated. In another example, H0F of gaseous carbon atom, it is found that the heat of reaction for the transformation from carbon graphite to gaseous carbon atom, it is 718 kilojoule per mole. So this is the standard state. Okay, so this must have to be taken as 0, and this one for delta H0F for carbon gas. Okay, so what is the heat of the reaction? This 718 is actually delta H0 of the product minus delta H0 of the reactant. What is the product? Carbon gas is the product and graphite is the reactant. For this one, it is assumed to be 0, and this one we do not know. So this is simply just this delta H value. Delta H reaction is nothing but H0F. So this way H0F of carbon, gaseous carbon, is calculated, and it is equal to be 718 kilojoule per mole. In yet another example, we have to calculate the standard heat of formation of carbon monoxide. Okay. We have already calculated oxygen atom has the H0F value 249 kilojoule per mole. We have also calculated the H0F value of carbon gas, which is 718 kilojoule per mole. Now we have to calculate the H0F value of carbon monoxide, CO. So what is the reaction? Now the reaction is carbon gas, okay, and oxygen atom. They combine to form carbon monoxide in the gaseous state. So we have to find out the H0F value of carbon monoxide. So we do not know this value. So we are just simply writing H0F of carbon monoxide here. But these values are known. They have already been calculated. This value is 718 kilojoule per mole and this value is 249 kilojoule per mole. Okay. So the standard heat of reaction is nothing but the difference between the delta H0 values of the product and the reactants. Okay, this minus this. Now the experimental value of the overall reaction, that means delta H reaction, which has been experimentally observed, is minus 1066 kilojoule per mole, 1066 kilojoule per mole, and this value is nothing but equal to the difference of the delta H0 of the product and the reactants. Now delta H0 of the product means what? Product is nothing but carbon monoxide, so it is nothing but H0F of carbon monoxide, so H0F of carbon monoxide. And delta H0 of the reactant means the H0F values of carbon gas and O. So this is H0F of carbon gas and this is H0F of O atom. Okay, these two values have already been derived to be 718 and 249 respectively. So these values are put here, but this value is unknown, and then we have got this equation: minus 1066 equals to H0F of carbon monoxide minus 718 plus 249. And by solving this, finally the H0F of carbon monoxide, that means the standard heat of formation of carbon monoxide, has been found, and it is found to be minus 99 kilojoule per mole. Okay, and last but not least, the example of formation of ammonia. So what is the heat of reaction, standard heat of reaction of formation of ammonia? So this is the equation for formation of 1 mole of ammonia gas. Okay, 3/2H2 half N2 equals to NH3. So the H0F values of hydrogen is 436. Since it's 3/2 moles, so this is multiplied. And for half mole of N2, H0F of N2 is multiplied by half. And this value is actually unknown to us. Okay. And standard heat of formation of ammonia for this reaction, the observed value is minus 1080.5 kilojoule per mole. By the same way, what we did in case of carbon monoxide, we can do this here also. That means standard heat of formation of ammonia, this value is unknown, but these two values are known to us. Okay, so these values have been just put here, and finally by solving we can get this value 46 kilojoule per mole. Okay, so this way we can find out standard heat of formation of any substance, as we have done in case of ammonia here, previously in the case of carbon monoxide here. Also you can do as a part of your practice the same for carbon dioxide, water, H2S, HCl, etc. Okay, and here is one question: how to calculate the standard heat of formation if the reactant molecule or molecules do not or does not exist in the elemental form. Okay, yes, that's a very valid question. If it is not at the elemental form, it is simply a compound. Okay, then how they are calculated? So we have to calculate the standard heat of formation of carbon dioxide, which is obtained from carbon monoxide. So carbon dioxide is not directly obtained from carbon and oxygen. It is actually two-step reaction, and finally we have to get this from carbon monoxide by reacting with one atom of oxygen, that means half moles of O2. Okay, so we have to write the equation like this: carbon monoxide in the gaseous form plus half oxygen in the gaseous form to produce 1 mole of carbon dioxide in the gaseous form. So these two values are known to us. We have just calculated. This is minus 99 and this is plus 249 kilojoule per mole. So this value, it can easily be calculated, isn't it? So the heat of the reaction is experimentally observed and it has been found to be 243.5 kilojoule per mole. So simple, 243.5 kilojoule per mole plus 99 minus 249. Okay, look, plus 99 minus 249 if this negative sign is multiplied here. Okay, this way it is found to be 393.5 kilojoule per mole. Okay, the same way. So just have a recap. Okay, have a recap. First of all, what did we do? We found the H0 value of oxygen atom. Okay, next time we have found the H0 of carbon atom in the gaseous form. Next we have calculated the H0 of carbon monoxide in the gaseous form. In another example, we have found the H0 of ammonia, and finally we have determined the H0 of carbon dioxide with the help of H0 of carbon monoxide and oxygen atom. Okay, so this way standard heat of formation of any substance can easily be calculated from the experimental values observed from any reaction. Similarly, the delta H value of any substance at any temperature can also be calculated. It is to be noted that the H0 values are actually delta H values at standard state and are not the state functions. Okay, this is very important thing. H may be a state function, but delta H is not at all state function. Okay, so that's all for this part 1 of thermochemistry. Thank you. Have a nice day.